Hello, this is our second really technical metallurgical podcast with Jack Lilly and Paul Rudd and Caelan. And we had a great deal of fun. Last time we did, how do you solve problems? What's a problem-solving methodology? This time we talked about heat treating and quenching. Spent a lot of time talking about how long to leave it in the furnace, how hot to get it, how to operate the furnace, and also how to quench it. How fast do I need to quench? What other quenches could I use? Salt water, oil, other things. So I think you might really enjoy this. Please let us know if you have questions or need more information. Look forward to hearing back from you if you see something that you really like or something you're interested in us doing. Thanks. I had made the point that a lot of our heat treating practices were based on the fact that we had really limited process control. So we used processes that had fairly robust results. And so one of the things we do is we will try to make sure that the casting gets completely hot. And so the reason we hold it in the furnace for a long time is not because the transformation from martensite to austenite takes that long, or even the dissolution of carbides takes that long. The reason we do it is because 40 years ago, 50 years ago, we only had one thermocouple in, and we weren't sure we had much uniformity in the furnace. And we could look in and see it wasn't that uniform, but if we left it in there long enough, all of the casting would get hot enough. And Paul was about to comment on that, I think.
Yeah, that's I guess that's one of my pet peeves when I go visit foundries is, in general, the condition of their heat treat furnaces. And especially door seals seem to be a real issue. People don't seem to, well, it really gets down to a question of routine maintenance. I don't think we do enough of it. We let our door seals go. We let our car seals go. And when you think about it, the castings that are near the door are going to be cold. The ones that are adjacent to a burner are probably going to be overcooked. And we lose a lot of energy that way. So, part of the problem, I think, with these long durations for holding times is because our furnaces really aren't sealed and protected well enough from the cold.
And one of the things that my kids have pointed out to me is that we historically only had one, maybe two thermocouples in the furnace, and being of our age, thermocouples were expensive, and so you limited how many you put in. They were like $10 a pop. and now of course they're still $10 a pop, but we're still acting like they're really expensive, and they're less than a drink or a cup of coffee. So if we put a lot more thermocouples in there, one of the only reasons people put two thermocouples in, because they didn't want to have to reheat treat the load when the one thermocouple went failed. You go, this is crazy.
It seems like, when we do the survey of the furnace, the furnace has just been maintained, it's in perfect condition, and we do the survey, and then 6 months down the line, we don't understand why we can't get the properties out of the test bars that we think we need, I think that's one of the things that's happened to us is we went along fat, dumb, and happy as long as we were heat treating 1-inch test bars. But when we get to the part about the 4-inch test bars, it's a different story. It takes more concise practice, better maintenance, better quenches, maybe some more alloy, things like that become very important. So the whole everything has really sort of changed when we got into the 4-inch coupon.
You had mentioned there doing the survey right after doing maintenance. Would you recommend doing surveys more often than once every 6 months, or would you recommend, like Raymond said, putting more thermocouples in the furnace so you can have I'll say more constant process control?
I think you should do surveys as frequently as needed until the conditions of the furnace are in good shape, and stay that way. If you don't have that reliance, then I think, you got to know that your castings are getting to temperature in all positions in the furnace, and without a doubt, you can't just guess at it. You've got to know that. So absolutely more surveys, but more maintenance. It's really a critical issue. And it's one of the things I was thinking about. A couple of things too. We don't really do the short cycle heat treating like we should. number one. And number two, I look at a lot of furnaces and they still have huge chunks of steel that are or what you set your racks on.
Yep.
This can be converted to ceramic, and you save tons and tons of money, and your heat treat cycles get shorter because your ramp up time is much faster with the ceramic than it is with these steel pillars that people are using all the time. So there's some recommendations anyway.
Yeah. Oh no, that's good. That's good. One of the projects we had with Frank Peters was you could tell that you were close to getting a temperature when the burner stops coming on.
Yeah. Well, that's another pet peeve of mine is these guys that make these controllers for the burners. They make sure that it's safe, that they will never go over the set point.
Yeah.
So what they do is they start slowing down the furnace well before the set point, which just aggravates the amount of time it takes to get the whole load up to temperature. Right.
Wow.
So what you need to do is put an artificial set point that's maybe 200 degrees beyond the set point to drive that furnace as fast as it can possibly go. And then it controls it. And once it gets anywhere near it, then you start to shut the burners off. In other words, you don't go over the set point, but you go with a much sharper curve. Much higher ramp up time.
Oh, I think that's right. And of course, thickness really matters, especially once you get over about 4 inches. So, Caelan, one of the things that we should put on the website with this webinar, Charlie put together a spreadsheet for me that lets you put in how thick it was. And if you brought the surface to temperature immediately, how long does it take for the center to get at temperature? And that's the absolute minimum time. That assumes that the furnace operates perfectly, but it really dramatically shows what happens as you get thicker and thicker. When you get up to the 8 and 10 inches, it really takes some time for the temperature in the center to get up there.
Yeah. Actually, the conduction of heat in steel is not that bad. Right. So, but if you start off, you should know, you should have thermocouples in these heavy sections and know what your furnace is capable of, because burner sizes are very, very different, right? How many million BTU per hour per burner, how much energy are you putting into that furnace will basically determine how fast that center section heats up. But you have to know that if you're going to try to short cycle.
So Paul, since this is for everybody under the sun, when you say big or thick, how big, how thick?
Well, I think I don't know, Jack can speak to that also, but I think generally this 4-inch coupon that everybody's agonizing over seems to be like a sticking point. So I think at least we need to know what's going on there.
I'd agree that 4 inches for sure, but in anything thicker. I haven't spent a lot of time dabbling below 4 inches, but in some of my not too distant work, we were looking at heavier sections, 8-inch sections in particular, and I learned how much I didn't know about heavy section heat treatment.
One of the funny things, one of the early surveys I did when I started working here was we'd started a heavy section group, so we were trying to figure out how heavy a section was. And George Harte was the one that said things get different when they're over 4 inches and they get a lot different over 8 inches. So that was always my sort of hip pocket answer. But I wanted to ask people, how big is a big casting? And so I got everybody to tell me in their shop what they thought a big casting was. And the only thing that was correlated to how big you thought your casting was the capacity of your crane. When it took more than half the capacity of your crane, then that's a big casting.
Well, everyone needs a bottleneck in a crane, in a shop. A crane or the critical crane can often be that bottleneck.
Yeah.
And sometimes you can surmount it with using multiple cranes to accomplish a single crane task, but that depends upon your layout and your equipment.
So one of the things I wanted us to concentrate on quenching, because I've got lots of questions that you both will know something about. But the first one is, I've heard numbers from anywhere from 30 seconds to 2 minutes is the absolute maximum time from getting from the furnace into the water. Is that size dependent? Is that alloy dependent? What's your understanding of how fast I have to get from the furnace into the water or the oil?
I personally, it's section size as far as I'm concerned. Okay. Small castings need to get there fast,
Okay.
And big castings, where you got sections that are like 6, 8 inches, whatever, you could take a long time getting there. It takes forever to get all that heat out of them,
Okay.
So I don't put any restrictions on heavy castings, but when you get into light castings, that's a different story. You really need to hustle them into the quench.
Don't you have to worry about some of the finer features, especially if they're hanging out on the edge of these heavy castings, cooling off before you get in the water?
I don't know.
Okay.
I don't know the answer to that.
Yeah.
If you have that problem, I would worry about it, but I would hope you would plan to not have that problem.
Okay. Yeah. Yeah. I mean, it's interesting.
You need to get everything fully submerged. I know there's a lot of been talk about transformation, and Paul made some comments about short cycle heat treat, and I wouldn't discount or dismiss that, but I've found more and more there are situations where the heat treatment cycle is driven more than by transformation.
No doubt.
And things like homogenization and things like that. So you need to use it's alloy specific, and there's different conditions for different alloys and so forth. But you really need to understand what you want to do microstructurally and have sufficient time and sufficient proof that you're doing that in order to be successful.
A lot of the high performance steels that we've been working with, the sweet spot seems to be around 4 hours. If you're less than 4 hours, you haven't gotten the complete benefit. And when you go over 4 hours, you begin to get some other precipitates or growth of phases or other things that begin to limit your ductility and toughness.
Well, and I point to some of Dave Van Aken's work, where he's working on completing the equilibrium transformation before going back and re-austenitizing to make sure you had no retained austenite, because what he showed was if you didn't do that, you'd have fine amounts of retained austenite dispersed. But it turns out it was all in the same crystallographic orientation because it came from the same parent grain. So when it started to grow again, they all grew together to make the same big grain again instead of a lot of new grains. So things like that again, it depends on what you're trying to accomplish, and you need to understand that and
so Jack, one of the
plan for the mission.
When we talk about short cycle heat treatment, that's normally about alloyed steels where we're trying to transfer it to austenite and dissolve any carbides.
Sure.
So it's a fairly uniform thing. In the high alloy materials, you're often trying to dissolve really odd intermetallic kinds of stuff.
Absolutely.
And
but
so,
I've just seen some issues with my new and limited exposure to low alloy steels that you might run into some pitfalls in that process.
Here's a thought, Jack. Most low alloy people that I've dealt with, and all my experience has been a prior normalize before you do the quench. And the prior normalize does several things. Okay, it reduces the stress that was caused at solidification, but probably just as important, maybe more important, is that it dissolves the carbides that are in the grain boundaries and the prior austenite grain boundaries, and puts that carbon and whatever it is back into solution. And that takes generally a higher temperature than what you would use in austenitize for a quench. And that's where the long cycle, I think, needs to be. I think dissolution is carbs. But when you're talking about the austenitize for the quench, I think that's something entirely different.
I agree.
That transformation happens very fast. It doesn't make any difference how long you hold it, because when you go into the quench, that's what's actually doing the performance. But holding it at temperature, I don't think accomplishes much. But that first normalize, that's really critical, very critical, especially from the standpoint of Sharpies.
So when you're talking about the higher temperature stuff, one of the things that Jack and the folks do in high alloy materials in order to make the quench more effective is, having dissolved all that stuff, they'll cool it off in the furnace a couple of 100 degrees to get a real kick in terms of quenching. So Paul, I think you and I had a brief conversation one time about using that in low alloy steels to optimize quench. Is that something that you've done in the past where you
take it up to like most 17? People would, what they will do, I mean, this is a practice that I consider as acceptable, is to heat rapidly up to, say, the normal come out of the quench, going into the quench water is generally around 1650 for low alloys. But generally, you can take it up to 1750 and ramp it up faster, right? And then when you get to 1750, then shut it back down to 1650 before you quench. So you don't put as much energy into the metal that you have to take out with the quench.
Sure.
Okay.
Sure.
Yeah.
Sure. Sure. I think that's right.
One other, I'm going backwards a little bit, but I agree with Paul's philosophy on ramping up and how there's things done in the control loops to limit overshoots, and there's a lot of emphasis on that will slow you down. But I would caution that you have to understand which specs you're heat treating to, because
Sure.
I know we've run into some severe constraints within NADCAP specs in terms of how big an overshoot you can plan in there. It gets really sticky with some auditors and some customers.
Yeah, I don't think it's ever been proven that you can heat a steel casting fast enough to cause a problem. This is
Don't
just
confuse me with the
specification
facts. The thermocouple went out.
Oh,
Yes.
Went high limit.
Paul, I always thought you could always heat them as fast as you wanted to. And George Harte convinced me that if you have a material like an chrome iron that's brittle, if you heat it fast enough, you'll break them into two pieces, because the outside is trying to
Steel Founders Society, guys. This is Steel Founders Society. This is a Cadillac of metals. We're not talking about irons here.
You can do that with
the only time I've ever heard where hoop stress is a problem with heating too fast is in pipes and tubes and stuff where you have hoop stress. Then you can heat that stuff too fast. But at casting, it's not like that at all. So I've never heard.
I would point out that heavy section duplex is an exception to that rule.
Well, sure, yeah.
If you've got a lot of secondary and tertiary phases on cool down from solidification, you got to be really ginger about how you heat that back up to not create a problem.
Yep. Good point.
But I agree. I actually, as a chemical engineer, thought you ought to run the furnace 100 or 200 degrees above the targeted endpoint to get the heat transfer rate up. But then you have to worry about overheating the surface. So you do have to be, but you could come up with a really sophisticated heating cycle where you went to very high temperatures to begin with and then backed off pretty fast. And that would really accelerate your heat transfer into the part. Yep. So,
but again, to Paul's earlier point, the same maintenance crew that's not maintaining door seals and car seals is the one who's probably maintaining your control system. So you got to be pretty careful about the tasks you put in front of people.
Yeah.
So I've got two questions about the water temperature in the quench tank. One of them is, how hot is too hot? And the other one that's really of interest to me is, have you ever tried ice or cold water to see if you could enhance the quenching? So first, hot water, 95 degrees, 100 degrees Fahrenheit, or do you want to lower than that?
What temperature are you talking about? Max temperature within the whole cycle or start quench temperature? Because a lot of our customers differentiate.
Oh, I do think they do, but I think the temperature you should never exceed. So the higher one of the two.
Yeah. To me, that's 90 degrees. And the reason I say that is Houghton, who makes all sorts of polymer quenches and fast quenches and oil quenches and all sorts of things, they've put out a list of the effect of each one of their quenches versus temperature. And once you get much past 90 with water, it starts exponentially decreasing the H value of the quench.
Sure.
So also, to me, it's not only the start temperature. It should be, as far as I'm concerned, somewhere between 70 and 90 for water, but it should be maintained throughout the quench, which means when you put the load in the quench, you need to start putting colder reservoir type water into the quench to keep it below 90 degrees. Okay. I don't think it does any good, especially in a small quench tank, to not add water to it as you're quenching, because the temperature of that water is going to go up very fast. So you're going to lose some H value there.
Yeah, I think that's right. And certainly the intensive quench people have shown one of the things you can avoid having dead spots in flow is by not having a full tank. And so you could imagine if you were making a single part like the digger tooth, you could come up with an intensive quench system where you were really spraying the water on hard enough that you didn't have a steam blanket and you'd get the optimal sort of quench that way. So cold water, though, have you ever tried cold water? It seems to me that we've never thought that was economic. So we've never really looked at really cold water, but cold water seems to me to be a potential for real opportunity for improvement. Have you ever tried that?
I've never tried it, but I don't think you want to get real cold water. I think you'll start seeing quench cracks that you're not used to seeing.
I would confirm Paul's observation. I've seen issues with cold winter startups on Monday after the quench tank's been sitting over the weekend and have problems that have been attributed to the water being too cold, to the point that several shops I've worked in have adopted putting in a dummy load to heat up the tank before you start making product.
Exactly. Yep.
So Paul,
in most foundries I've worked in, we had like a big scrap casting or something that we would stick in the furnace on a Monday morning, especially during the wintertime, to get the water temperature back up to 70 or somewhere near that.
Okay.
Yep.
So let me ask you a question, Paul, because you worked for Briggs. One of the things that Briggs you routinely seem to advocate was if you had a big heavy section casting, doing a slack quench where you put it in the water, you got it down below about 500 degrees and you pulled it out and let it do some auto tempering. Have you ever done that? Is that a practice that you would still do, or did you not believe it?
I think it's feasible from a metallurgical standpoint, but I wonder how well we would control that as a production tool.
Okay. I'm unaware of anybody who does it today unless there's some historical part they had where it was already put in the procedure and they still take it out of the water early.
But most people
you do have to take it out of the water somewhat early. You should not let your castings get down to the quench water temperature. You need to pull them out somewhere around, for low alloys again, somewhere around 250 degrees.
Okay.
You don't want to quench them cold. And another factor, obviously, is once they're quenched, they need to go to the temper furnace as fast as possible. If you leave them sitting around, the residual stress from the quench will cause cracking. So there's two things to avoid quench cracks.
How big of a time window do I have? You say as fast as possible. Is that 10 minutes? Is that 10 hours? How much?
I think it should be to the point where you schedule the availability of your temper furnaces. I think it's that important. In other words, there should always be capacity for the temper furnace, at the proper tempering temperature. That should all be resolved before you start scheduling your quench. You should know what the tempering furnaces are. That's going to be more important.
So you're saying an hour, 2 hours, something on that order, not.
Yeah, sure. Absolutely. And if you can do it 30 minutes, you're better off.
Okay.
And it's a non-issue if you're not seeing quench cracks, but if you leave them sitting around with all that stress on them from the quench, sooner or later you're going to wind up with quench cracks, especially if there's a big change in section from heavy to thin. That's a real stress raiser. Yeah. So
is that primarily for the high performance steels that you used to make for ground engaging tools, or does that like an 8625? Is that?
Yeah, quench cracks generally, anytime you're approaching 30 points of carbon or above, you're going to be susceptible to quench cracks, whether it's an 86 or a 43 or whatever it is. The magic is the carbon content, I think.
Okay. Yeah.
So if you're quenching an 8625, it's not going to have the same propensity to crack as say an 8630.
Yeah, Bob Shepard used to track DI, and he could correlate at Harrison Steel the incidence of cracking with the DI content. So basically, that's the higher your carbon and alloy content, the more propensity you have for cracking. And so that makes sense. And of course, Ken Murphy for under riser cracking used the welding rules to come up with carbon equivalents that you use to do preheat as well. And both of those seem reasonable, but they both go to what you're talking about, the composition with carbon being the most important factor. Yeah, that makes sense. Have you ever tried salt, the sort of saltwater quenching to try and enhance quenching?
Yeah, Houghton makes a product. It's called Aqua Rapid A, and it's nitrate and nitrite salts.
Okay.
And you can get your H value, and we did this going way back to Shreveport.
Oh, wow.
When we were doing a lot of GET work for Caterpillar, we use this quenchant, was called Aqua Rapid A, and you mix it with water and everything like that. H value is somewhere around 5.
Wow.
5. So, that sounds real exciting and everything. The problem with that is that these salts corrode everything they touch. everything, all the pumps, they all had to be brass and bronze, and pillars and everything had to be very specially alloyed to make sure that you didn't corrode everything. And then the castings come out with salt all over them. So what are you going to do about that? But if you want, you can alter the quench severity by adding stuff to the water for sure. Wow. But not the polymer. Polymer slows it down.
Yeah, the polymers. Of course, that was one of the big things that I looked at, 35 years ago when I started working on the quenching project. And polymers were seen as an alternative so that you could get rid of your oil quenching. Right. Oil quenching was always problematic. Not only was it mess, it got oil everywhere. So you had people slipping and tripping and crap on everything.
And they catch on fire.
Gunk. Then you had fires every time you put a casting into it. And you hope that you got it under the water fast enough that the whole thing catch on fire. So you had the fire thing.
And, heat treating was much more interesting back then.
But of course,
it still is some places.
Yeah, I'll tell you what, I pity the people that still oil quench. I don't know why they're doing it. I have no idea.
A lot of it's legacy customer demand. And what you have
to do. The customer's doing it. He's got the wrong alloy selected. Okay. And we know, I think through a lot of experimentation, that when we get 100% martensite from a water quench, we get really the best combination of strength and toughness. And when you oil quench, you're just not going to do that. It's not going to happen.
Yeah, Pinson Valley that we use for some of our heat treating, they have an oil tank, and I don't know of any. Grady Foundry in Milwaukee was the last one I knew that retained an oil tank, and that's been gone 20 years. So I don't know of any steel foundries that still have an oil.
Going back, Raymond, going back 30 or 40, 50 years ago, 4140 was the engineering grade.
Wow.
It had 40 points of carbon, it had relatively good DI, but it had to be oil quenched with 40 points of carbon. There was no way around it, But through time, and I think gaining knowledge about water quenching and how it's done to keep from cracking parts, it just sort of took over, and people switched from the 4140s and things like that to the 86 series with lower carbon contents. Quench them as hard as you possibly can, get good sharpies, get good tensils, good strength.
So, Jack, I'm going to ask you a question. You're the only one that probably has much information on this. Nitrogen. When you do atmospheric heat treatment and then you use nitrogen to quench, how thick of a section can you quench and how effective is it?
You're talking like a gas fan quench in a vacuum furnace?
Yep.
I'm going to honestly tell you, I don't know. Okay. I've seen some data. I've never really analyzed it. I know there's people who claim it's effective, and it appears to be effective enough, and that's all on fairly thin sections.
Yeah, my sense has always been that it's more commonly used for the austenitic or stainless grades, where you're really just trying to solution treat them and avoid some of these intermetallics, rather than actually quenching for properties. But I don't know, Caelan, you worked for Timken. Did you guys do any nitrogen quenching? Did you have customers who did it?
Um, I don't know if customers did, but we didn't do any at the plants. It was basically all water quenching.
Okay.
One of the questions that I have is you've mentioned quench severity, H value several times. Are you always targeting the highest quench severity possible? Are there certain minimums you're looking for? And what are the characteristics of the castings that determine what sort of quench severity do you need? So like, do you need a higher quench severity for heavy sections, or what's your thought process?
Personally, I think you ought to try for the highest quench severity you can get with water and the size of the castings that you're working with. And understanding the quench itself is part of the hardenability factor, and the other, of course, is the chemistry, right? So I think they're doubly important, and I think we've seen this, especially with these 4-inch coupons that we're making, that we didn't have enough DI. You know, we had lean alloys making 1-inch test bars. Everybody was happy, but when they switched to these 4-inch bars, and you take the specimen at 1/4 T, that's a different world. And I personally, I think that requires more DI and the very best quench that you can possibly imagine, you know, to get the very best properties you can, because the engineers are sitting there thinking they've got the same strength level all the way through the section, and that's just not true. You know?
Yeah,
So one of the challenges with quench severity, though, is there's a diminishing return as you get higher and higher H value. Um, so what's the practical limitation? Because you can go to H value of infinity and you get, I forget how much of a benefit compared to an H value of 5.
Well, that's a good point. But, you know, I think maybe more important at this time is to try to figure out a way that you can determine H value, okay, economically, and to do it periodically so that you know your quench tank is staying in good condition, you know. So, you know, I'd thought about this for quite a while. Could we as Steel Founders Society buy some 2-inch bar, 2-inch round bar from Nucor, buy a whole heat of it or something, and chop it up and send it to the members who, you know, who are interested, or, you know, sell it to them, or whatever we have to do. But basically determine the geometry on it. And if we know those two things, and we put them in and we do the curve, you know, through the section, the hardness traverse, we should be able to determine quench severity. And if we had a tool like that, then we could compare ourselves to other quenches, you know. But you know, if I think, and we would use, just see that as a big possible tool, or maybe there's some better way to find out what your quench severity really is. I don't know, but I do know that you can do it with a round bar. It has to be fairly lean, because you don't want it to quench you don't want martensite all the way through the bar. It has to be fairly lean.
We had looked at, in that original project, we had done some 1300 alloy grade, which is just a carbon manganese grade, to try and evaluate the quench severity. But we'd also used a stainless steel pipe with a thermocouple down into a stainless bar that was 4 or 6 inches long with a center thermocouple in it. And that gave us really good results. When you start looking at 2 inches thick, you don't get much of a response in terms of your H value, because you've got too much thermal conductivity to overcome. And so you get a fairly sluggish response. But when you had a 1-inch bar, we got some really pretty good things. And that was relatively inexpensive to do. I mean, it was just 304. My engineering analysis was that using 304 meant that it stayed austenite all the way down, which was fine. That's basically a reasonable thing to get at the H values you're looking at. And so it'd be interesting to look at that. We also looked at the flow rate, and you and I talked about that. So John Griffin has a little propeller thing you put in. And the problem with that is you get numbers all over the place, depending on what direction you turn it. And it's sort of like measuring hydrogen or oxygen with one of the active probes. And I remember Fritter looking at oxygen, and the numbers bounced all over the place. And he thought the instrument was unstable. And doing the reoxidation work, I realized no, that's actually happening in the steel. The liquid metal passium has all kinds of different oxygen potential. I even looked at the anemometer, where you actually just heat a wire up and you measure the voltage and amperage that'll go through it. And that changes depending on the flow rate past that wire. But that never seemed to be very useful in terms of trying to characterize it. So I, like you, the thing I liked was the 1-inch probe. We used to have a tube furnace and replace the glass tube with a Inconel tube. And that way you could get the tube up to 1800 degrees with 110 volts and stick the probe in. And since you got it on a thermocouple, you know when it gets to 1800 degrees, and you could dunk it into the quench tank with a load or without a load. But I like your suggestion that we may want to redo that 40-year-old work to see where people are today in terms of their quenching and heating. And it ought to be something we could do.
It's gotten to be more important with these heavy sections, you know.
Absolutely.
And
Absolutely.
taking the test bars at 1/4 T, that really changed the game.
Yeah. And what I'd like to do next time is talk about the problems of heavy section test coupons. I have been absolutely overwhelmed for over 3 years dealing with foundries with the challenge of looking at heavier section test coupons. And there's a lot of snakes in the bushes that people are unaware of. For example, if you go not just to the thermal center from the bottom to the top of a wedge, if you go to the thermal center from the edge to the edge of a wedge, you're going to end up with microporosity that limits your ductility, even though Niyama says you've got a sound bar, even though you don't have any indications, you're going to get microporosity. And so you're going to really struggle to get the ductility. Yeah. And we've got a lot of data where you can see by location that as you get closer and closer to that thermal center, the ductility and toughness begin to drop off pretty rapidly. And so I think that would be worthwhile talking about.
Yeah, I think so. And I've talked to a couple of people, you know, I feel very strongly that the thermal gradient is really critical to these test bars. So the question is, why not put a chill on the bottom of the test bar mold and create more temperature gradient to get a finer interdendritic arm spacing, which is, I think, is what the issue really is.
Yeah.
I've seen the same thing. You get your strength levels seem to be okay, but you fail the ductility.
Yep.
Elongation or reduction. Usually elongation is the bad one.
Sure.
But you seem to fail the most when you take test bars out of a section like that.
Yeah, the reduction in area tends to be such a low limit. Historically, in writing the standards, you'd appreciate this. In writing ASTM standards, if you pass the elongation and yield strength, we knew that was a good heat. So the yield strength was easy to pass if you met the yield strength, and reduction in area was easy to pass if you met elongation. And that's the way those standards were written.
Yeah.
So, yeah.
I see a lot of test bars coming out of these big sections that don't pass, and they don't pass even the strength level. And the reason they didn't pass is because the hardness wasn't there, you know, to begin with. So, you know, at a bare minimum, when you take one of these test bars out of a heavy section, you need to Brinell it before you break it. You know, if it's not high enough, you can forget it. You're not going to make it. You know, it's not going to do it. That's a straight relationship, right?
Absolutely. Let's plan to do just a whole section on test bars next time we get together. Anything we've forgotten to talk about, Paul? Or
one thing I'd like to recommend regarding quenching is the submersible impellers systems, you know, that actually, you know, the whole gadget, the whole motor, everything goes underwater with the quench. When you use those things, and what I've seen is you can make your quench do what you really want it to do. You can direct the water flow. You can make sure that you don't have dead spots. You can do that with a submersible impeller. So that's one thing that I think we ought to at least consider, at least throw it out there and let people know that it's available.
Oh, that's great. That's a good idea. And Jack, you had something. Yeah.
Yeah, I just want earlier we were talking about oil, and you said no one was doing oil. I was trying to articulate that WC does oil and does it every day. There's a certain amount of the product line that requires it for customer spec, and it's a product line that changes are arduous. So I don't foresee it being replaced soon or easily, but they do it all the time.
And Jack, I only ask you about nitrogen, but you're an expert on the really sophisticated nickel-based alloys, duplex alloys, those kinds of things. And typically in those materials, you heat it up to dissolve everything, and then you quench it so nothing else dissolves back out. And so it seems to me that no one's ever really talked to me with great concern, other than for the duplex heavy sections where I can't cool it off fast enough, even with quenching it, to get the properties in the center. And in solidification modeling, we had Beckerman look at how thick of a section you could make and still expect to get properties in the middle. And it seems to me his estimate was up in the 10-inch kind of section, but that's probably too ambitious. So what about quenching duplex steels, and what about quenching these nickel-based alloys? What are things that people might need to think about in terms of doing that work? How long can it take to get it in the water? How aggressive does the quench need to be in H factors, that kind of stuff?
I think the quench needs to be as aggressive as possible. And I think you got to figure out what the customer expectations are. A lot of those high alloys, people are purchasing to specs like Norsoc, where they have some pretty rigorous both heavy section coupon and weldability testing and things like that. And I know there's a lot of people that have other members that have some pretty strong opinions about maximum section sizes achievable on different alloys, because you got to cool it fast enough to make sure you're not forming secondary and tertiary phases in the center line. Now, from a corrosion point of view, practically, I think if you have a pretty good solid skin, you should be okay. But again, don't confuse me with the facts. They want you to prove corrosion at the center line too.
Oh, that's just like the Navy wanting the toughness in the center of a 13-inch steel casting, and you're going, if you need fracture toughness in the center of that section, something really bad is happening somewhere else, and you got some bigger problem. When you were talking about corrosion and the possibility of second and third phases you were concerned about, when we were doing all that validation work for some of the alloys with Lundin, it became pretty clear that Sharpie was a better, more discriminating test for the effectiveness of heat treatment than the corrosion testing. And I just wanted you to have a chance to say whether or not you think that's still true. If I'm trying to develop the heat treatment, I'm trying to evaluate its effectiveness. Is Sharpie V-notch a good discriminating test to see how well I've heat treated these materials?
I believe that it is. It's been a while since I looked at Carl's work, but I was active in the committee when it happened, and I think he did a really nice job. And I think basically he showed not only that it was an effective test from a physics point of view, but from a sampling point of view. You look at a microstructure, you're looking at a small area field of a sample, where at least from a Sharpie you get some volumetric exposure as well, at least for the number of samples you're fracturing.
That was our session on heat treatment, both furnace control and quenching, and how to be more effective. If you have any questions, please let us know. Thanks.